Okay, let's begin our fourth lecture video. So in this lecture video, we're gonna talk about Neyman-Pearson lemma, and likelihood ratio test. So the first topic is Neyman-Pearson lemma. To go into Neyman-Pearson lemma, let's do a first quick review of what type 1 error is and type 2 error is. So let's do a quick review. So type 1 error, what is type 1 error? Type 1 error is denoted as alpha, and it is the probability of reject H null given H null is true. And what is type 2 error? So type 2 error is denoted as beta, so it is the probability of not reject H null given H null is not true. So we also have one more terminology, which is power. Power is no new thing, it's just 1 minus beta. It is called power in statistical theory. So why do I review these two concepts, type 1 error, type 2 error? Because in this lecture, we would like to control alpha. Alpha is type 1 error at a certain level. Then to maximize 1 minus beta. So the above goal can be realized by Neyman, Pearson, lemma. Neyman, Pearson, lemma. Okay, so to talk about Neyman-Pearson lemma, we firstly classify hypothesis testing. So in our previous lecture, we have done single-sided, which include right-sided test and double-sided test. So single-sided test is, for example, H null mu greater or equal than 0, H1 mu less than 0. The double-sided test H1 mu equal 0, H null mu equal 0, H1 mu not equal 0. H1 is H alternative. We just in this time I switch to another notation H null H1, and these two are called composite hypothesis. Hypothesis testing. We have done this in previous lectures. Composite hypothesis testing. And another category is simple hypothesis testing. So what is simple hypothesis testing? For example, H now is just theta equals theta 0. H1 is theta equals theta 1. And such hypothesis is called simple hypothesis testing. And Neyman-Pearson lemma considers this kind of hypothesis testing. Let's see what Neyman-Pearson lemma is. Neyman-Pearson lemma. So Neyman-Pearson lemma is, let's firstly consider random sample capital X1 all the way to capital Xn ID following some distribution f x given theta. So this is some distribution small f, and theta is parameter, population parameter of interest. Then Neyman-Pearson lemma is as follows. So Neyman-Pearson lemma is for any given alpha, the test which maximizes 1 minus beta at H1, which is alternate hypothesis, H1 theta equals theta 1, is the following decision rule with rejection region. So the first rejection region as a set the likelihood function of theta 0 in H0, H now, over the likelihood function of theta 1 smaller than k, some constant, and the next question is what k is. Really is k some constant, so k. So Neyman-Pearson lemma actually has two steps. So the first step we write we find the likelihood function at theta and the likelihood function at theta 1. We calculate the likelihood ratio like this. And the Neyman-Pearson lemma says for any given alpha, the test which maximizes 1 minus beta at h1 theta equals theta 1 in the following is the following decision rule with the rejection region as a set. So rejection region itself is a set. The set is the first part of Neyman-Pearson lemma. It has such set representation. The likelihood ratio less than k. And k is some constant. The next step is to determine k. So let's see how to determine k. So k is determined according to alpha by the following formula, which is the probability of a set theta 0 divided by likelihood theta 1 greater than k, our rejection region. This is the first step. We write, less than k, given h now is true. We set this probability as alpha, then we can solve k. So the next step is to determine k, and k is determined through this equation. We set this probability of this set should be equal to alpha. So this is Neyman-Pearson lemma. Neyman-Pearson lemma told us that by these two steps, first step you compute likelihood ratio with numerator being likelihood function evaluated at theta 0 and denominator being likelihood function evaluated at theta 1, and the reject region should be in this form, and k should be determined by the formula, which is we set alpha equal this probability of this, the pre-specified rejection region, given h now is true. And the Neyman-Pearson lemma tells us that for any given alpha, the test determined by the following two steps maximizes 1 minus beta. So that's the main conclusion of Neyman-Pearson lemma. So Neyman-Pearson lemma has so the key to remember Neyman-Pearson lemma is it has two steps. First step, you write the rejection region in this representation, and then to complete the first rejection region, to complete the representation of rejection region, you have to determine k, and k is determined through the second step. K is determined by this formula to determine k. Set this probability of this event given h now is true to alpha. Then we can claim by Neyman-Pearson lemma that such test constructed by the following two steps maximizes 1 minus beta. This is what Neyman-Pearson lemma says. Okay. So maybe you forget what likelihood function is. So let's do a quick review of what likelihood function is. Review of likelihood function. So likelihood function is given a realization small x as a set of the realizations of random sample small x1 to small xn. The likelihood function of the parameter of interest, the likelihood capital L of theta given x, is just the product I from 1 to n, the probability density function of small xi given theta. So this is the definition of likelihood function. So we have reviewed what likelihood function is. It's just a product of PDFs. Okay. And final remark of Neyman-Pearson lemma is that so for any given alpha, the test which maximizes 1 minus beta, and we gave it a name. Give it a name. The name is most powerful test at alpha, because for any given alpha, we maximize is 1 minus beta, and 1 minus beta has terminology as power, so we call these two aspects as most powerful test at alpha. So this is a restatement of these two parts of Neyman-Pearson lemma. We have a specific terminology in statistics theory, which is most powerful test at alpha. Okay, so we have finished the introduction of Neyman-Pearson lemma. Let's see an example of Neyman-Pearson lemma. And recall our goal of today's lecture is, in this lecture we would like to control alpha at a certain level, then to maximize 1 minus beta. So given alpha equals some value, to control alpha at a certain level, we can set alpha at some small value, then we would like to maximize 1 minus beta. And Neyman-Pearson lemma told us that we can use two steps. First step, like rejection region as such a set. And second, we should determine k by this formula. Then we can state that for any given alpha, we can find the maximization of 1 minus beta, and we call such test most powerful test at alpha. So recall our goal of today's lecture. By Neyman-Pearson lemma, we have finished our goal for the simple hypothesis, because recall, as I mentioned, Neyman-Pearson lemma considers such simple hypothesis testing. How about composite hypothesis testing? So for the final goal to this lecture, we have finished the part simple hypothesis testing by simply apply Neyman-Pearson lemma. So next, let's first see example of Neyman-Pearson lemma. Okay, let's do remark. So Neyman-Pearson lemma can be abbreviated as NP lemma. NP lemma finds maximum of 1 minus beta, which is power given some alpha for simple hypothesis testing for h0 theta equals theta 0, h1 theta equals theta 1. So now let's see an example of more complicated hypothesis testing. Can we apply Neyman-Pearson lemma to some complicated cases? Let's first see the first important example. How about h0 is mu here, theta equals mu, the population mean. So theta now is mu 0, but theta 1 is not simple. Simple means just one value. H now, in this case, we specify mu greater than mu 0. So it is no longer a simple hypothesis testing. This is also a composite hypothesis testing. So to apply, so in this question we would like to apply Neyman-Pearson lemma. To apply Neyman-Pearson lemma, NP lemma, we need to first transform this hypothesis testing. Firstly, transform the hypothesis testing. So the hypothesis testing is H now mu equal mu now mu 0, H1 mu greater than mu 0. Because we would like to apply Neyman-Pearson lemma. Neyman-Pearson lemma handles the situation of simple hypothesis testing. We transform it to simple hypothesis testing. So for null hypothesis, it remains because it's single value. So for the alternative hypothesis, we specify mu equals mu 1 and mu 1 greater than mu 0. And we can say, so how to transform this? We can specify each time we can specify a mu 1 which is greater than mu 0, and the original hypothesis is H1 mu greater than mu 0, but we don't specify what mu is. But if we would like to apply Neyman-Pearson lemma, we have to relate this composite hypothesis testing to the single hypothesis testing. How to accomplish this? We can make a union over what? Union over mu 1 greater than mu 0 and mu equals mu 1. So we can write in this way. So H1 is mu, and we union mu 1 greater than mu 0. Then this alternative hypothesis is equivalent to the original one because we union over all possible mu 1 greater than mu 0. Then such union alternative hypothesis is equivalent to this one. So these two are equivalent. And to apply Neyman-Pearson lemma, we select one fixed value of mu 1 which is greater than mu now, and we see this pair of hypotheses to apply Neyman-Pearson lemma, which means what we do is consider H now mu equals mu now, H1 mu equals mu 1. We mu 1, and as I have said, mu 1 is greater than mu 0 because the equivalency between this original alternative hypothesis and this union of one pre-specified mu1 greater than mu0, and this becomes a simple hypothesis testing. We can apply neyman NP lemma. So to apply NP lemma, our first step is write rejection region. So NP lemma rejection region is in this form: the likelihood ratio less than some constant k, and in our scenario, theta is mu, so mu0 divided by likelihood function evaluated as mu1 in alternative hypothesis less than k. Here you have to keep in mind that here k is just is a notation constant, is a notation for some arbitrary constant which needs to be determined. K is a notation for some arbitrary constant. So what k is actually is not that matter. K is just notation to remind you that it is some constant. So we don't really mind what k is, but we use k to denote some arbitrary constant. If k is some arbitrary constant, we just use this notation to record it. So it's just for constant. It's not a fixed value. It's some arbitrary constant. So you need to keep in mind in our derivation later. And for this set, let's first write this set. So since this is set, we are concerned with set equation. So what is set equation? So set equal, for example, x greater than 2 is equal x 2x greater or 2 or y 2y greater than 4. So they are equal. So later for the set equation, you should keep in mind that the set equation means set equal in this sense. So this is quite important in our derivation for set. So now let's specify what the set is actually is. So the first part is we need to specify the set for rejection region. This equals So before I write this, let's first review what is the likelihood function for normal case. So let's recall the PDF of normal. So recall our original random sample is Okay, I did not say the random sample for this hypothesis testing. Let's specify here. Let's consider capital X1 all the way to capital Xn ID normal mu sigma square, and sigma square is assumed to be known. Then let's review the PDF of normal distribution. So the PDF of small xi given mu, since sigma square is known, we don't write sigma square. So its PDF is in this form 1 over 2 pi sigma square exponential of negative xi minus mu squared divided by 2 sigma square. This is the PDF of normal. So what is the likelihood function evaluated at mu? It's just product of PDF I from 1 to n f small y given mu, and we just plug in this PDF I from 1 to n square root 2 pi sigma square 1 over this square, no square, exponential negative small xi minus mu, sorry, this not yi, xi xi minus mu squared divided by 2 sigma squared. And we spread this product out, so the result is 1 over square root of 2 pi sigma squared raised to the power n exponential negative summation I from 1 to n yi minus mu squared divided by 2 sigma squared. So this is the likelihood function evaluated at mu. Then after review the likelihood function of normal distribution, let's write this. The likelihood function evaluated as mu 0 divided by likelihood function evaluated as mu 1 less than k as a set. As a rejection region, it is a set. Let's write set equation. Set equals as a set in the sense of set. So let's plug in. So see the likelihood function evaluated at mu 0 and mu 1. If you plug in, then this factor, this constant will cancel. What remaining is this part. For numerator, this is mu 0. For denominator, this is mu 1. So we just plug in exponential negative not y xi small xi. So plug in small xi minus mu 0 squared I from 1 to. We don't write this from 1, we just summation. Keep in mind from 1 to n squared divided by 2 sigma squared divided by exponential negative summation xi minus mu 1 squared divided by 2 sigma squared less than k. So these two set are equal. And so k is just a notation to, so although k changes between this set and this set, but we don't mind what k is. Recall, k is just notation to record. Just notation to record some constant, some arbitrary constant. Just notation to record arbitrary constant. arbitrary constant k. So k changes, but in the sense of set equal and in the sense that k is just notation to record arbitrary constant, we still use k, although k is changing. The value of k is changing, but we recorded that k is some constant. This is our way of writing this. And then for the division for exponential, we can simplify it as follows. So this set equals exponential summation xi minus mu1 squared minus summation xi minus mu0 squared divided by 2 sigma squared, whole thing exponential less than k. And then let's do some observation, because this exponential function is controlling this whole thing in the parentheses, and exponential itself is a monotone transformation, which means if you take log on this side and log k, then the set does not change. It's like what? It's like x greater than 2, it equals x exponential of x greater than exponential of 2. So they are equal. And since k, as I mentioned, k is just a notation to record some arbitrary constant. So k is just a constant. It changes. We don't mind. We always write k. So this means we can delete this part. We don't need this part because in the sense of set equal, they are equal. And divide some, and this part divide some 2 sigma squared, divide some positive number is also a monotone, and does not change the set function. We can also eliminate this part, and then the right hand side also keeps a constant. Although k changes, but we just use it to record some arbitrary constant. We keep writing in this way. So what do I mean by this? Then after such observation, you get what? You get we don't need exponential and we don't need 2 sigma squared. Since sigma squared is known as constant, the set function is simplified as the following: summation I from 1 to n xi minus mu1 squared minus summation I from 1 to n xi minus mu0 squared, and this whole thing less than k. So k is just notation to record some arbitrary constant. We just write in this way, although k is keep changing during this duration, and such equal sign means set equation. It is equal among sets, just as this example. And then we also write equal. And what to do next? The next is we spread this two summation of square term out. So we make xi squared minus 2 mu1 xi plus mu1 squared minus xi squared minus 2 xi mu0 plus mu0 squared, and do subtraction, and we rearrange. We got what? you can check by yourself later. It's just simple algebraic operation. You get this equals 2 times yi xi, sorry, xi times mu0 minus mu1 plus this I from 1 to n plus n times mu1 square divided by mu0 square less than some arbitrary constant k. Okay, then we also do observation that this part is just constant. So plus constant, we move it to the right hand side. So k also an arbitrary constant. We move it to right hand side. So what is left is this part on the left hand side. So we can further simplify this set. Is 2 mu0 minus mu1 n times x bar, small x bar, smaller than some arbitrary constant k, because we just move this part to the right hand side and it go into the k, because k requires some arbitrary constant. We just keep writing k because we need to find k in the second step. Okay, and since this part is also monotone, but this part is, so mu1 is greater than mu0, so this one is negative. So if you make it go into the right hand side, you have to reverse the direction of the inequality. So which means this is small x bar greater than some arbitrary constant k. So we have finished the first step for Neyman-Pearson lemma. So the Neyman-Pearson lemma, step 1. In step 1, in this specific case, we got what? We got the likelihood of mu0 divided by likelihood of mu1 less than k. In the sense of set equation, it is just x bar greater than k. So this first part of application of Neyman-Pearson lemma in this specific case. And the second step for Neyman-Pearson lemma is what? Second step of Neyman-Pearson lemma is to find k by the following formula. The following formula is what? That's right. We set alpha equal this probability, the probability of this, the likelihood evaluated as mu0 divided by likelihood evaluated as mu1 smaller than k, given h now is true. And this is equal what? Because in the first step we have find this useful representation in the first step. So we write here this probability of capital X bar, because this is probability. To quantify probability, we substitute small x bar with capital X bar greater than some arbitrary constant denoted as k, given h now is true. So h now is what? H now is mu equals mu0. The next step is to do standard normal transformation. So capital X bar minus mu 0 divided by sigma divided by square root of n greater than k minus mu 0 divided by sigma divided by square root of n. And this is what? This is z, standard normal, which means we can find z, which means k minus mu 0 divided by sigma divided by square root of n equals z alpha. And then we conclude that k equals mu 0 plus z alpha sigma divided by square root of n. So we have finished the two steps in Neyman-Pearson lemma. The first step, we find the set of the rejection region. The second, we use this formula to find what k actually is. K is mu 0 plus the alpha sigma over square root of n. Then we can restate the conclusion of Neyman-Pearson lemma. So we conclude that rejection region is equivalent to decision rule. So rejection region is what? So small x bar greater than k. K is mu 0 plus z alpha sigma divided by square root of n. This is rejection region. Such decision rule. Rejection region means if x bar is greater than this, then we reject h null. Otherwise, we do not reject h null. So this is what rejection region means. So we can conclude that this test is most powerful test at alpha, because this is the main conclusion of Neyman-Pearson lemma by two steps, step 1, step 2. Step 1, step 2, Neyman-Pearson lemma guarantees that it is most powerful at alpha. Recall what we have said about Neyman-Pearson lemma. So Neyman-Pearson lemma, for simple hypothesis testing, Neyman-Pearson lemma by two steps, we can state that for any given alpha, the test which maximizes 1 minus beta. So this is called the most powerful test at alpha. So this is our conclusion. Our conclusion here. Okay, recall this most powerful test at alpha for what? For h null, mu equal mu 0, h1, mu equal mu 1. But next we do another observation that observe mu 1 is arbitrary. Mu 1 is greater than mu 0. Which means our original hypothesis mu equals mu 0. H1 is mu greater than mu 0. And since mu 1 is arbitrary and mu 1 greater than mu 0, what we can claim? We can claim that the rejection region, which is a set small x bar greater than what? Greater than mu 0 plus z alpha sigma divided by square root of n is also most powerful at alpha for what? For the original test. Original test is a composite hypothesis testing. It is not simple hypothesis testing because H1 has inequality. So Neyman-Pearson lemma help us to find most powerful test at alpha for composite hypothesis testing. That is why Neyman-Pearson theorem is called a lemma, because it can be applied into some conclusion in composite hypothesis testing. So this is the first observation. So for the second observation, so this is just one composite hypothesis testing. It is composite hypothesis. But do remember we are concerned about single-sided testing in our previous lectures. Recall single-sided testing. We're interested in test what? We're interested in testing in this form: mu equal or less than mu 0, and h1 mu greater than mu 0. And here, this composite hypothesis testing has only one equal sign in h null, but here we have one more less than sign in h null in single-sided testing. So can Neyman-Pearson lemma help us to find most powerful test for single-sided testing? The answer is yes. Neyman-Pearson lemma is very powerful. It can help us in this setting. So let me give you the fact. We first transform. So in this time we do not transform. So the first step is that if we let's think this way, consider h null mu equal mu 0, h1 mu greater than mu 0, which is this case. We have done this in this example. Consider this. Using this, we know that we have known in this previous example, we know that small x bar greater than mu 0 plus z alpha sigma divided by square root of n is most powerful. That's alpha due to NP lemma. But how does this relate to our single-sided testing? Recall what we have done in the second step. Recall in the second step of NP lemma, we set alpha equal probability of capital X bar greater than the key which needs to be determined given mu equals mu 0, this probability as alpha, and we find k. We find k as what? K as mu 0 plus z alpha sigma divided by square root of n. And let me tell you a fact. The fact is that the probability of capital X bar greater than mu 0 plus z alpha sigma divided by square root of n given h null. So in this case h null is just a single value. This is h null. But because in this case we change our situation to such h null, so our h null changes not equal. So h null is what? Is mu equal or less than mu 0. Then the fact is that this probability is less or equal alpha. And this is a very fortunate result, this fact, because we want to control the type 1 error as small as possible, and this fact tells us that it can be even smaller than alpha. Then we can conclude what? We can conclude for single-sided testing, NP lemma guarantees us that it is most powerful test. And this time we don't say at alpha, we don't say at level, we say at level alpha, because here is not equal, is less. So with the help of this fact, we conclude that the rejection region x bar greater than mu 0 plus z alpha sigma divided by square root of n is most powerful. The most powerful at level alpha for what? For single hypothesis testing. So here we add one more word, level, because for Neyman-Pearson lemma we just set equal to alpha, but here with the help of this fact states that this probability is less or equal than alpha. Then we add one more terminology as level. So this terminology corresponds to this fact. So it's still most powerful at level alpha for this single-sided testing. So at this stage, we have seen the powerful application of Neyman-Pearson lemma. So let's do some summary. Summary is like the NP lemma. Use NP lemma to find rejection region to use NP lemma to find rejection region. How to use NP lemma is two steps. So to use NP lemma by two steps to find rejection region, to construct a test, then the test is most powerful for single-sided testing. Of course, also include simple hypothesis testing, but that one is extremely simple. We don't write it down. So at this stage, we can state this quite important summary that to use NP lemma application is just two steps to find rejection region. Then the test is most powerful for single-sided testing. So for the classical theory of statistical hypothesis testing, one important conclusion is this: use NP lemma with two steps to find rejection region, then the test is most powerful at level alpha.